Last time we talked about how oxygen and carbon dioxide are transported in blood. Now let's talk a little bit about some of the neural control mechanisms of breathing, as well as the coordination between the respiratory and the cardiovascular systems. So one of the things we've talked about before is when you have tissues that need perfusing, for example, peripheral tissues, we're going to have blood vessel dilation at those tissues so that we can bring oxygenated blood to those tissues and move carbon dioxide out of that area faster. We're also going to change our respiratory rate depending on our exercise. So we're going to change our rate and depth of respiration depending on what we're doing. And I have to sort of apologize for the microphone or lack thereof. The computers here are 7 and 8 years old respectively, so things are beginning to fail on them. I just hope that I can coax them through to the end of the semester. At any rate, so let's look at some of the gas transport. So, for example, when we have alveoli in the lungs that are oxygenated, we're going to direct our capillary blood flow to those alveoli because we want to pick up that oxygenated blood. Now, this thing right here makes no sense. This is somewhat ambiguous in the slide. I don't know what the editors were trying to do when they put the slide together. The Pearson editors, I think they took this completely out of context because rising carbon dioxide levels in the alveolus is actually going to shunt blood flow away from those alveoli towards alveoli that are oxygenated so that you can pick up the oxygenated, or I should say pick up the oxygen in the blood, so you want the blood to go to the oxygenated alveoli, and then eventually when you off-gas all the carbon dioxide, the alveoli that were filled with carbon dioxide will now, when you take your next inhalation, be filled with oxygen. And so basically we were constantly shunting the blood flow by dilating the arterioles and capillaries around the alveoli. We're shunting the blood flow to the alveoli with the most oxygen content. And so we're going to be constantly shifting this blood flow around. And so carbon dioxide levels are going to control our bronchoconstriction and bronchodilation as well. So not just in the arteries and the capillaries, but also, for example, if we have a lot of carbon dioxide, what we're going to do is we're going to increase ventilation. So we're going to increase our respiratory rate and we're going to dilate our bronchial tubes so that we can bring more oxygen in. All right, so now let's look at the neural control. So we've got, if you recall from our previous chapters and our last semester, when we looked at the brain and the brainstem, we know that we have our respiratory rhythmicity centers in the medulla oblongata, and these are further assisted by the apnea and pneumotoxic centers of the pons, and all of these are highly interconnected with each other, with a reticular formation, and some other areas of the brainstem that are going to be working together to regulate respiration. And most of it is involuntary, but you do have voluntary control. For example, when you want to get that shiny quarter from the bottom of the swimming pool, you will hold your breath to go down there to get it. So obviously you have some control. And if you walk into a really nasty, noxious smell, you probably hold your breath until you can get through it. So yes, we have some voluntary control over our respiration, but when we don't think about it, basically the respiratory rhythmicity center of the medulla oblongata, they're paired centers, and we'll see that they're made up of different groups of neurons. These are going to be regulating your breathing with the assistance of the two sets of centers in the pons that are the apnea and pneumotoxic centers. All right, so we've already talked about these, and these are going to be involved in our respiratory reflexes. We have several respiratory reflexes that we'll look at, for example, if coughing and sneezing, you get an irritation somewhere in here. You're going to have to clear your throat or your nose of that irritation, or maybe a noxious gas. But all of this is going to be taken care of for you by the respiratory centers basically within the reticular formation, the medulla oblongata, and the pons. And these are going to regulate our respiratory muscles. As you recall, inspiration is going to be under the control of the diaphragm and the external intercostal muscles. You can also recruit other muscles such as the pectoralis minor, such as the sternocleidomastoid, and so forth. But these will not be involved in what we call eupnea or quiet breathing. These The main muscles for inspiration are going to be your diaphragm and your external intercostals. And these are going to be completely, well, this is an active process, but when we exhale, it is a passive process. We simply stop stimulating these muscles and they relax. And so the diaphragm pushes back up into the thoracic cavity and the external intercostal muscles relax, and that allows the ribs to close in on themselves. All right, so when we look at the medulla oblongata and we look at our respiratory center, our respiratory rhythmicity center, we'll find that we have a dorsal respiratory group. And this is going to be responsible for inspiration. This is going to function both in quiet breathing when just the diaphragm and the external intercostals are involved, as well as forced breathing when we start recruiting some of these other accessory muscles. The ventral respiratory group is only going to come online when we have forced breathing. It has both an inspiratory and an expiratory center. And basically what we will find is the inspiratory center is going to help recruit these external, or I should say accessory muscles for breathing, for inspiration, and then when it comes time to exhale, when we want to exhale further, and we recruit, say, our abdominal muscles and our internal intercostal muscles and so forth to help force the air out of the lungs, then our ventral respiratory group is also going to be involved in that. So quiet breathing is basically going to be activity of about 2 to 3 seconds of the dorsal respiratory group. That's going to stimulate your diaphragm and your external intercostals, and then they'll basically shut down for 2 to 3 seconds, usually about 3 seconds. So inspirations maybe 2 seconds, expirations about 3 seconds. And this just allows those muscles to relax, and this is what you do normally during your day-to-day things. Forced breathing is when we're going to increase the activity of the dorsal respiratory group to bring the ventral respiratory group online. And that's going to activate your accessory inspiratory muscles. And there's a nice slide for that that shows sort of the cyclic patterning. Then after inhalation, your expiratory centers, and these are going to be within that ventral respiratory group, are going to stimulate active exhalation. Interestingly, you have a reciprocal inhibition here. So when the inspiratory muscles are working, the expiratory muscles are inhibited, and vice versa. All right, so the apneustic and pneumotoxic centers of the pons are paired nuclei. The apneustic center is going to be involved in inhalation, and the pneumotoxic center is going to be mainly involved with exhalation. And so these basically are going to regulate the rate and depth, help regulate the rate and depth of respiration. So we're going to have the apneustic center, which is going to be providing inputs to the dorsal respiratory group and the respiratory rhythmicity center of the medulla oblongata. The pneumotoxic centers, as we said, are going to inhibit the apneustic centers, and they're going to promote in exhalation, and this is partially through that reciprocal inhibition. So sometimes the exhalation is passive, and that's just simply inhibiting the diaphragm and the external intercostals or any of these inspiratory muscles, or it can be active where it promotes the activity of some of our accessory muscles that will further constrict the space in the thoracic cavity. All right, so we're going to have interactions, obviously, between the ventral and dorsal respiratory groups that's going to establish the basic pace and depth of the respiration, and the pneumotoxic centers are going to modify that. So we will also see that higher brain centers can affect this. For example, the cerebrum, limbic system, hypothalamus. When you have an extremely emotional situation, the hypothalamus and the limbic system may input their input into this system. So people who get really, really scared, they might, for example, before a big presentation or something, before walking on stage in front of 500 people, they might start hyperventilating. And that would be simply because these higher centers are exerting a top-down control. Likewise, your cerebrum can also take control. For example, when you're diving underwater and you need to hold your breath, you need to stop breathing for a bit. So you need to go into a period of what we call apnea, which is without breathing. That is what apnea means. So basically, these higher brain centers can hijack or take control to a certain degree of this breathing process. But if, for example, you put the entire brain and everything above the midbrain to sleep, these the pons and the medulla oblongata would take care of your breathing for you completely. So there have been people who've had severe brain damage who basically been have pretty much died, but their brain centers can still keep them alive. All right, so sudden infant death syndrome occurs usually in young infants during a very critical time of wiring of the system. So there are respiratory reflex patterns that are being laid down, and so sometimes there are some connection problems between the complex that's regulating the pace of breathing and the respiratory centers, and so sometimes this causes these infants to stop breathing. And this usually happens between 2 and 4 months, I think it is, of life, usually in late fall or winter. So infant death syndrome is one of those strange things that is not entirely understood, but it kills about 2,500 kids, something like that, a year. So it is a consequence of, well, researchers think it's the consequence of some of these connections being disrupted while these brainstem connections are being laid down. All right, so we have some respiratory reflexes. For example, we've got chemoreceptors that are going to be responsive to CO2 and oxygen, the partial pressure of these things, as well as pH in the blood plasma and in the cerebrospinal fluid. And we'll find these are going to help regulate. This is going to send the feedback, usually via the vagus nerves and the glossopharyngeal nerves. It's going to send feedback up to these respiratory centers. And we'll see that what's going to happen is we're going to have these receptors, these baroreceptors and chemoreceptors all over the body that are going to give us information about the partial pressures of dissolved gases and the pH. This is going to be important because it's going to help us regulate our breathing and coordinate breathing and cardiovascular function. So we will see that we have got chemoreceptors in the carotid sinuses and the carotid bodies and the aortic bodies, as well as in the medulla oblongata to sense the concentrations of dissolved gases and pH in the cerebrospinal fluid. So that way we will know, for example, if the perfusion to the brain is not receiving enough oxygen. So, for example, if you have too much carbon dioxide, that's going to be picked up in the carotid bodies as well as, or carotid chemoreceptors are in the carotid bodies. Yes, that's correct. Okay, so it's the baroreceptors are in the carotid sinuses. Anyway, so the carotid bodies are going to pick up this increase in carbon dioxide, and it'll also be detected in the cerebrospinal fluid. And that's going to signal that we need to pick up our respiration, off-gas some of this carbon dioxide, breathe in more oxygen, and get better perfusion, obviously, or better oxygenation, I should say, to the brain. Better oxygenation and better perfusion to the brain. Now, we also are going to have baroreceptors, and these are going to be in the aortic and carotid sinuses, and these are going to be sensitive to changes in blood pressure. So going back to our question on the lab practical, if you stand up too quickly, then those pressures are going to drop. And some people have a vasovagal syncope where their peripheral resistance doesn't catch up to gravity, and so the blood pressure will drop precipitously and they don't get perfusion to the brain. So we have our respiratory centers and our vasomotor centers are going to be very important for regulating blood pressure, so once again we get proper perfusion to the brain. We're also going to see that we have some stretch receptors in the lungs, and this is going to respond to changes in lung volume. So during forced breathing, for example, when we expand our lungs to our maximum possible capacity, we're going to get to a point where they really can't expand any further, and trying to do so would damage them. So there's going to be a stretch receptor response that will shut down inhalation when the lungs have reached their maximum capacity. Likewise, you can exhale to the point where you cannot exhale anymore. And once again, you've got receptors in the lungs that tell you that your lungs are too small. You've pretty much pushed all the air out of them that you possibly can, and that is going to force you to inhale. So we've got some reflexes that basically are going to regulate how much we can stretch or compress our lungs. We're also going to have reflexes that are going to respond to irritating chemical stimuli or physical things, dust, insects, whatever, getting in the nasal cavity, the larynx, or within the bronchi. So what happens if you breathe in a nasty chemical? Sometimes you might have some laryngeal spasms, which will close the larynx and the glottis so that you can't breathe. Unfortunately, if the chemical stimulus is so noxious, it can actually close this to the point you can't breathe, and then you'll die as asphyxiation before you can even get out of the noxious stimulus. But typically, for example, when you sneeze and you cough, you will experience a very short moment of apnea, where basically you stop breathing, you build up a lot of pressure in your lungs, you close the glottis will close as pressure builds up, and then you will expel whatever contents of your lungs that you can, the air, in order under high pressure, in order to force out whatever this noxious stimulus is. So if you've ever swallowed an insect accidentally and had it go in there, you'll probably cough it back up. All right, so there are other things that can change your rate of respiration, pain, one of which body temperature changes, and abnormal visceral sensations can all change your respiratory rate and depth. All right, so when we talk about the chemoreceptor reflexes, these are going to be monitoring cerebrospinal fluid and blood. So the ones that monitor the cerebrospinal fluid are on that in the medulla oblongata, right along that cerebral aqueduct and the fourth ventricle there, and these are the ventrolateral surfaces of the medulla oblongata, and these are going to respond to the partial pressure of carbon dioxide and pH in the cerebrospinal fluid. And these things usually go hand in hand, because when carbon dioxide goes up, pH goes down, because things are getting acidic in here. So this generally means that we need to inhale more oxygen and get rid of some carbon dioxide. So this will typically, if we detect more carbon dioxide in the CSF than usual, then we will breathe faster to get rid of it. Another interesting thing that we will say is that carbon dioxide is the main driver of our reflexes. Oxygen, not as much. So usually, as long as we're getting rid of and off-gassing carbon dioxide well enough under normal circumstances, then we're going to be breathing in enough oxygen to take care of our needs. And unfortunately, this isn't always the case. If you're in a very low oxygen environment, then sometimes you can breathe all you want. You're not going to get much more oxygen. But under normal circumstances, under normal atmospheric conditions where you would be, then if you're off-gassing your carbon dioxide correctly, then more than likely you're probably going to get good alveolar ventilation, where you're going to be bringing in enough oxygen. Now, when you stimulate these chemoreceptors, you're going to increase the depth and rate of respiration, and that's so that you can basically bring in more oxygen and get rid of the carbon dioxide. Hypercapnia is an increase in the arterial carbon dioxide concentrations. This is going to stimulate the chemoreceptors in the medulla oblongata, and hopefully what this is going to do, if you have too much carbon dioxide, usually from holding your breath or not breathing properly, then that will stimulate. Once you have stimulated these chemoreceptors, that's going to send signals to your respiratory centers to increase breathing rate and depth. Now, hypocapnia is too much or too little carbon dioxide. So basically, hypocapnia comes from hyperventilation. So if you are hyperventilating, you're going and what ends up happening is you breathe in a lot of oxygen and you're breathing away a lot of carbon dioxide. So basically you're getting rid of the carbon dioxide almost as soon as it's formed. And of course, carbon dioxide is one of the main drivers for this respiratory circuit, the regulation of it. So if you get really low on carbon dioxide, that's going to make it really hard for the respiratory centers to be properly stimulated. So hyperventilation causes hypocapnia. Hypoventilation is the cause of hypercapnia, and hypercapnia just means too much carbon dioxide. It usually comes from not breathing enough. So hyperventilation is breathing too quickly, and you often see this when people get nervous or when they get upset or if they're emotionally distressed about something, they'll start breathing really, really quickly, and they off-gas a lot of CO2, and this leads to hypocapnia. And so this is going to stimulate your chemoreceptors to decrease respiratory rate. And so what people do to ameliorate the situation often is breathe air that has a higher concentration of carbon dioxide, or you can hold your breath. So a lot of people, they'll put a paper bag up to the mouth of somebody who's hyperventilating, and then they'll breathe just the exhaled air. So they keep breathing this CO2 rich air, and they're bringing the CO2 concentrations back to normal. All right, so this just basically shows some of our homeostasis mechanisms. So it just basically shows what happens when you have hypercapnia, too much carbon dioxide. Then you're going to stimulate your chemoreceptors, and that causes an increase in carbon dioxide, and so the pH is going to be lower, obviously, in the cerebrospinal fluid. So you're going to stimulate the respiratory muscles, stimulate the chemoreceptors of the medulla oblongata will stimulate respiratory muscles. That will increase your respiratory rate so that you can get rid of the excess carbon dioxide. So then that restores homeostasis. Now, when we have the opposite, when we have decreased arterial carbon dioxide, that is, we have hypocapnia, well, then we're going to have inhibition of we're going to have decreased, basically, carbon dioxide, therefore increase in pH. We're going more alkaline. So that's going to inhibit our arterial chemoreceptors. And so we're going to decrease the stimulation of the chemoreceptors, and therefore both of these things are going to inhibit our respiratory muscles. So our respiration slows down. And hopefully we can hold on to some of that carbon dioxide a little bit longer, so that we can then return our carbon dioxide contents more to normal levels. All right, so we've got several reflexes, baroreceptor reflexes. Now remember, baro is pressure. So we have got carotid and aortic baroreceptors, and these are going to affect blood pressure, or monitor blood pressure, I should say. So remember, in our carotid sinuses and our aortic sinuses, we have these baroreceptors that are going to detect distension of these vessels. And so if you have too high a blood pressure or too low of a blood pressure, that is also going to affect our respiratory centers. So when blood pressure falls, respiration is going to increase. For one thing, you're going to need to increase the oxygenation in the blood, because you're not going to have enough oxygen in the blood to perfuse the tissues with oxygen. So when blood pressure increases, respiration can decrease. All right, so we have this thing called the Herring-Brewer reflexes, and these are basically going to be baroreceptor reflexes that are involved in forced breathing. And this is what we were talking about earlier, about expanding the lungs too large or letting them get too constricted. So the inflation reflex is going to prevent the overexpansion of the lungs. So if you're trying to breathe in as much as you possibly can and hold that in your lungs, eventually you'll get to the point where you could overstretch your lungs, and so the inflation reflex is going to stop you from going past that point. And the deflation reflex is going to do something very similar. It's going to inhibit the expiratory centers when you've off-gassed all of your air within your alveoli, and so basically that's going to stimulate the inspiratory centers during this major lung deflation. When you've gotten about as small as you can get your lungs, then beyond your control, you're going to start to breathe again, because it's basically preventing you from over deflating your lungs. All right, so we've already talked about our protective reflexes somewhat. We've got the protective reflexes will be triggered by receptors in the epithelium of the respiratory tract. So when you get toxic vapors, the first thing you want to do is hold your breath. Chemical irritants, even mechanical stimulation, like when the bug gets in there, and if you've ever swallowed food wrong and you get something sitting on your epiglottis or your glottis, and you keep wanting to cough it to clear it out. So all of these kinds of things can trigger these protective reflexes, and these include coughing, sneezing, and laryngeal spasms. So when you breathe in a bunch of pollen, which we're probably all doing about right now, then sometimes that can trigger sneezing. So we get a lot of sneezing and coughing this time of year. All right, apnea is when we suspend respiration. So anytime, let's say you're diving underwater to get that penny from the bottom of the swimming pool, that's apnea. In fact, free diving, where you don't use a regulator or tanks, is called apnea diving. And we also have apnea. People have sleep apnea. So sleep apnea is when people stop breathing for whatever reason. It can either be a closure of the throat due to mechanical problems, closure of the soft tissue over the passageways there, or it could be neural. Some people have basically neural stimulation of these respiratory centers in the brainstem will stop functioning. So a lot of times, and there are different kinds of sleep apnea, but this can lead to all kinds of problems if not treated properly. So a lot of people who have sleep apnea will go on what is called a CPAP machine. So they will have this respirator that's forcing air, or this mask that's forcing oxygen into the back of their throat to keep everything open and to keep oxygen flowing. So apnea is not just a period of cessation of breathing just for these reflexes, but anytime we have a cessation of breathing for whatever reason. So if you sit here and hold your breath, that would be an example of apnea. So basically, we use apnea when we have these reflexes to clear our passageways. So for example, let's say a bee flies in there or something, heaven forbid. Let's just say it's who knows, you get some pollen or something in there. Then that's going to stimulate these receptors in the larynx and in these passageways. And so what's going to happen is your glottis is going to close and you're going to build up sufficient pressure in here during a period of apnea when you're not breathing, so that then you can cough or sneeze, and you can sneeze almost 100 miles per hour. So this is one reason people are worried when we have a pandemic and a spread of a virus, because you can spread a virus a very long distance from a sneeze, because sometimes that expectorant or that stuff that you're sneezing out can go, close to 25 feet away. All right, so the laryngeal spasm is when the airway temporarily closes. You can have a laryngeal spasm when you're trying to close your throat from mechanical stimulation or chemical stimulation that's noxious. So if you're basically, it's trying to prevent things from getting into the trachea. So the laryngeal spasm usually happens if you're presented with really noxious vapors, or if you get something that's irritating or stimulating the area around the glottis and the epiglottis. And here again, that is to prevent anything from entering into the trachea. All right, we have voluntary control of respiration. We've already talked about that. We've also talked about higher centers such as the hypothalamus that can have control or exert some control over respiration. So we've talked about the fact that emotional stress can activate the sympathetic nervous system, and of course that will cause you to breathe faster. It will cause your bronchi to dilate, and parasympathetic division would cause your bronchoconstriction and would also cause you to breathe more slowly. So also anticipation of strenuous exercise. Not only can it increase your heart rate, but it can also increase your cardiac or your respiratory rate as well. And here again, this is usually sort of a top-down control of the sympathetic nervous system. If let's say you're standing on the start line before a race and you're expecting to go full bore when you have your mass start of your event, then your breathing rate and your heart rate has already started to modify itself to meet the demands of that exercise.